In this video, we're going to review acids and bases, and then we're going to explore acids and bases from the perspective of grade 12 chemistry. The first portion of this lesson should be you going to watch the video lessons here, the little video snippets, to review the concept of acids and bases in terms of their properties and in terms of real-world examples. So you watch the video in the handout, you click there, it's also with the QR code here. You fill out the properties of acids and bases as a review from grade 11 chemistry, and you write out some real-world examples of acids and bases. The second part will consist of you watching this little video here to review the pH scale, basically from 0 to 14, with below 7 being acidic, above 7 being basic, and 7 being neutral. So you watch that quick video, make a few notes about it, and then you'll be ready to proceed to the next part, which is here. So part A was a basic review of acids and bases, and then part B is going to be another review, but more guided with this handout here. We're going to review acids and bases in terms of how you saw them in grade 10 and grade 11. So in grade 10 and grade 11, you learned about acids and bases from the perspective of the Arrhenius theory of acids and bases. And so under that theory, an acid was defined as any substance that produces hydrogen ions, H+ ions, when you dissolve it in water. So if you take HCl and you dissolve it in water, it should ionize, basically become ions, to make H+, and then some Cl-. The reason we say ionize is because this is a molecular compound, a covalent compound where there's no ions, and then these are converted into ions, H+ and Cl-. But it's this H+ that's being produced that makes this an acid here. And under the Arrhenius theory of acids and bases, a base is a substance that produces hydroxide ions, hydroxide, not hydroxyl. Hydroxyl is organic chemistry, OH, covalently bonded to a carbon chain. Hydroxide ions when dissolved in water. So NaOH, for example, would dissociate to make Na plus AQ plus OH minus AQ. And I didn't say ionize because these are already ions. In essence, a better way to write this would be as if I had the solid and I put the solid in water, then it would become Na plus AQ plus OH minus AQ. And this would, in theory, be a solubility equilibrium as well. But we won't go there. Right now we're just going to focus on the idea. How you learned it in grade 11 was that the Na plus produced the NaOH dissolved in water to make OH minus, Na plus, and this OH minus is what makes it a base. Now, there are several limitations with this theory. The first limitation is that there are some compounds that are basic, but they don't contain hydroxide. So under the Arrhenius theory, essentially any base would have to contain hydroxide to make hydroxide. But there are some compounds like ammonia or carbonates or bicarbonates that actually are basic. They have a pH above 7, and they don't contain hydroxide. So Arrhenius theory can't explain that. And the other thing about Arrhenius theory is that it only allows for acids and bases in aqueous solutions. So that means water always has to be around, but it doesn't really always have to be around to have acids and bases. So these are two main limitations that the Arrhenius theory can't really explain. So when a theory can't explain something, we have to use a different theory. Now keep in mind, doesn't mean this theory is necessarily wrong, it just means that it's not the most complete, and it works for now. But in grade 12, we're going to take a look at the Bronsted-Lowry theory of acids and bases, and we're going to take a look at all those associated concepts. So we're going to start defining acids as proton donors. So an acid is a substance that donates a proton. And when I say a proton, I mean a hydrogen ion, H+. So in this situation here, we have HF, AQ, plus H2O. Our HF is going to be our acid, and what it's going to do is it's going to donate this H to this water. And so the F will now be F minus AQ. Every time you lose one H, you become more negative by 1. And then the water would become, it gained an H, so H3O plus AQ. And this here is called hydronium. So hydronium is what happens when water gains an H through an acid. So when we measure the concentrations of hydrogen ions in a solution to see how acidic it is, we're actually measuring the concentration of hydronium ions in a solution. H plus does not truly exist in a solution by itself. It's not stable. It'll always connect to something. And in our cases here, we're going to connect to water. So this is what truly exists, not this. But we still sometimes write the H3O plus as H plus, just for shorthand. Another thing to notice about this equation here is that the water is liquid. That makes sense. It's our solvent. But we also have our two-way arrow, and that will be important soon. But in the Bronsted-Lowry theory of acids and bases, we're going to represent a lot of acids and bases as an equilibrium. Now, if an acid is a proton donor, well then a base is a proton or hydrogen receiver or acceptor. So it receives the H+. So here we have ammonia, which is a base, and here we have water. So in this situation here, water, I'm going to write it as HOH, is going to be giving away an H to ammonia. So that ammonia will become an H4, and when you gain an H, you become positive by 1, AQ, plus OH minus AQ. So notice that this is a hydroxide that's made, even though ammonia doesn't have OH. What's happening is the ammonia is receiving the H from the water. That's creating an H4 plus, and then the OH minus is produced, and that's what makes the solution basic. So under Bronsted-Lowry theory of acids and bases, an acid is a proton donor, a base is a proton receiver, and this helps to explain why the NH3 is a base without even having the OH present. So those are our new definitions. Now we're going to take a look at the ideas of conjugate acid-base pairs. So let's go take a look at this reaction here. In this reaction, we'll have a base reacting with water. And so the water will give away an H, we'll lose an H to the base, so the base will become BH plus AQ, again because H has a positive charge, it's a proton, so when something attaches to it, it becomes positive by 1 more. If you gain more H's, you be more positive. If you lose more H's, you become more negative. And the water will become OH minus AQ. So this was our base. And if you think about it carefully, water gave away an H. So water, under our new definition, is acting as an acid. So this is a base, this is acting as an acid here in this direction. But if you go the reverse direction, look at what's happening here. The BH plus would give its H to OH to remake water. So the BH plus is now acting as an acid. So you'll notice that the B was a base, but the buddy that received the H plus on the other side is now acting as an acid. So these two would be called conjugate acid-base pairs. This is the base, its buddy on the other side, if you did the reaction in reverse, would be called its Ca, its conjugate acid. Water, H2O, is acting as an acid. Now, because it's receiving this H, would be acting as a base. So this is the conjugate base of water. So in this Bronsted-Lowry theory, each base acid has its buddy on the other side that acts as the opposite on the other side if you did the reaction in reverse, because you're rewinding essentially. So let's try to take a look at this question here. Determine the conjugate acid for HCO3 minus. So what we're telling you here is that HCO3 minus in this question, because we want you to find the conjugate acid, is acting as a base. So HCO3 minus, we're going to make it react with water. We're going to put our double arrows, and we want you to find the conjugate acid. So because we want you to find the conjugate acid, that means this is acting as a base. If this is acting as a base, it's receiving an H from water. So when it does that, it becomes H2. Now we were minus, so it becomes CO3, not plus, but CO3, because we're minus, you add 1 plus, so that becomes just 0 charge, plus OH minus. And if you played this in reverse, well then this would give an H back to this. So the conjugate acid of the base HCO3 minus is H2CO3. So the conjugate acid would essentially have one more H than the base. Let's take a look at the conjugate base example now. So here we have HA plus H2O. This is going to be our acid in this situation, as an example. It's going to give an H to water. Now because water is receiving, in theory, in this theory, water is acting as a base. Now, this is simply relational, okay? The water as a solution or as a substance is neutral, but it's acting as a base in this Bronsted-Lowry theory. So now, when the HA loses an H, it's going to become A minus because it lost an H plus, AQ, plus the water is going to become H3O plus AQ. If you played this in reverse, the A minus would receive an H, making that a base. So this is the conjugate base. So this is the conjugate, this is the acid here, and its buddy is this conjugate base here. So these two are conjugate acid base pairs. Now water was a base. This is acting as a conjugate acid because it would give H plus to go back in the other direction. So these are conjugate acid base pairs, with this being the base and this being the conjugate acid. So in our next question, we're going to have to find the conjugate base of HCO3 minus. So what that means is that we're telling you in this question, because we're looking for the conjugate base, this is going to be acting as the acid. So if you write HCO3 minus plus water, this is going to give, acting as an acid, it's H to the water, so we'll have CO3 2 minus now, because you lost an H plus, it was minus C4, now it's 2 minus, plus H3O plus. If you went in reverse, this would accept an H from this. So this is our acid. This would be the base, the conjugate base. So the conjugate base of HCO3 minus is CO3 2 minus. Essentially, the conjugate base has one less H than the acid from which it was derived. So this is the conjugate acid base pair here, and then there's another conjugate acid base pair there, but we're focusing on this specifically with this. This is our conjugate base. And so in this theory, the idea of acids and bases is somewhat a relationship depending on who gets the H and who donates the H. So to finish off, what we just saw here in this portion is that conjugate acid base pairs are two substances related to each other by the donating and accepting of a single hydrogen ion. To truly be conjugate acid base pairs, they must differ by only one H plus. Just like HCO3 minus and CO3 2 minus, there's only one H plus different. Here, H and H2, only one H plus difference. So, knowing that, try to label this equation here with the terms acid, base, conjugate acid, and conjugate base. Pause the video, try it, and then we'll take it out. So, in this reaction, we have this substance here reacting with water to produce H3O plus and C2H3O2 minus. Now, notice that H2O became H3O plus. That means that it must have received an H. So an H went from there to here. So if H2O received an H, that means it was a receiver, so it was acting as a base, and its buddy on the other side would act as a conjugate acid if it went in reverse. Now, since this one here gave away an H, it's acting as an acid, and its buddy on the other side would receive an H when going in reverse, so this one is a conjugate base. So this is the conjugate acid-base pair over here, and conjugate acid-base pair there. So this is the acid, this is the conjugate base of that acid, this is the base, and this is the conjugate acid of that base. Our next practice question over here is H2CO3 AQ and HCO3 minus AQ are considered conjugate acid-base pairs, CBP. HCO3 minus AQ and CO3 minus AQ are considered CBP. Explain why H2CO3 and CO3 minus are not considered CBP. So why are these two not considered CBP? But this and this are, and this and this are. But these two are not. So, hopefully you had time to think about it. You paused the video, you tried it out. You can see that they differ by two H pluses. CBP differ by only one H plus. So that's why they're not considered conjugate acid-base pairs. So next we're going to take a look at another definition that will help, that is more clear using the Bronsted-Lowry theory, the idea of amphiprotic or amphoteric. So there are some substances that are able to act as a Bronsted-Lowry acid or a Bronsted-Lowry base. So an acid or a base in the Bronsted-Lowry Bronsted base theory, depending on the situation that they're in. So if you take a look over here, HCO3 minus reacting with H2O, the H2O donated an H. So that made HCO3 a base here. And then it made water an acid here. Now if you look at this reaction, number 2 here, if you look at the products here, it looks like this donated an H and this received the H. So in this case, this is the acid and this is the base. So it looks like HCO3 minus can act as a base and can also act as an acid, depending on the circumstances. But it looks like water can also do the same thing. So any substance that is capable of acting as an acid or base, according to our Bronsted-Lowry Lowry acid and base theory, is called amphiprotic or amphoteric. They can do both, and it really depends on the circumstance, and you'll be given some guidance as to how to figure that out. So, knowing that definition and knowing the examples that we just saw, you have to try this question out yourself here. Explain why CO3 minus AQ is not considered amphoteric. Not considered. So hopefully you had a chance to think about it. CO3 minus, remember, to be amphoteric, you must be able to be an acid and a base. If you're a base, you must be able to receive H plus. CO3 minus can definitely receive H plus. You could take an H plus from water. I'm not showing the whole process, but it becomes HCO3 minus. Now, to be an acid, you must be able to donate H plus. And it's probably clear that CO3 minus cannot, because it does not have H plus to donate. So that's why CO3 minus is not considered amphoteric. But HCO3 minus was. It could donate this, or it could receive an H to become H2CO3. And so that was based on our definition of amphoteric and amphiprotic. And now you're able to apply that idea conceptually. So in this video, we saw that you had to review acids and bases properties and pH scale very quickly using the snippets provided. We then did a quick overview of the Arrhenius theory of acids and bases. We then introduced you to the Bronsted-Lowry theory of acids and bases, where acids are defined as proton donors and bases as proton receivers. And we spoke about the idea of hydronium being formed rather than H+. And we're representing a lot of these acid-base reactions now with equilibrium arrows because they're going to reach equilibria. We also saw conjugate acid-base pairs and the idea that whether you're an acid or a base is more relational in the Bronsted-Lowry theory of acids and bases. And we learned about the terms amphiprotic and amphoteric in these videos and did some conceptual practice problems. In the next video, we're going to take a look at the strength of acids and bases.